Hello everyone, and thank you again for watching this video. This is actually the first of a series which will revolve around the topic of strength and power training in sport and exercise, one of the main pillars of SNC with a large range of applications among a variety of populations, youth athletes, normal population, so trainees commonly encountered in sports clubs, gym, or for outdoor activities, and obviously athletic competitive populations. Well, the lecture itself will be structured into three main phases, where the first one will be dedicated to define some basic rules, some basic definitions with regard to muscular strength and the specific elements which should be known whenever planning or prescribing resistance training exercises for a specific target population. In the second phase, second part of the presentation, I will introduce the main factors and mechanisms affecting the muscular strength production from a neurophysiological perspective, mechanical perspective, psychological perspective, and as a consequence, I will introduce the main training variables which should be taken into account when planning and implementing resistance training programs. Finally, I will share with you some of the most common guidelines and recommendations for resistance training and exercise prescriptions, which are commonly defined by established organizations like the United Kingdom Strength and Conditioning Association, the British Association for Sport and Exercise Science, and the American College of Sport Medicine. Well, to begin with, first of all, we all know that strength or force production is the result of sequential steps which start off with the planning, with the designing, with the programming of the movement itself, which takes place in the central neural system, where the brain areas or motor areas dedicated to the movement planning activate specific pathways which run across the peripheral neuromuscular systems and finally end up at peripheral level, at muscular level, with a series of actions which ultimately end up with the so-called contraction, which is the effect of sliding movements between the known contractile proteins, the actomyosin cycling action, so the effects of sliding movements between the actin and myosin proteins. So once the actin and myosin bind to each other, so are coupled to each other, they slide together, and as a result they create tensile forces, and these tensile forces are then applied from the muscles on the tendons, which attach specifically at given points of the skeletal system, which ultimately allows to generate movement around the joint axis. So in this slide you can see the specific configuration of the elbow joint, where is depicted the biceps brachii muscle, which is one of, let's say, the primary movers of the elbow joint, is a flexor muscle, and as you would imagine, this muscle allows to move the the front arm through the axis running across the elbow joint, allowing a flexion extension movements of the upper limb. So, in summary, these forces generated by the muscles and transferred through the tendon units to the bones where the muscles attach allows to generate the so-called joint torques, which is a combination of forces and the lever arms of each muscle and the attaching tendon unit on the bone, which determine the rotation and ultimately the movement of a specific joint. The two most important rules, if you like, we should take into consideration and always remember when planning and prescribing exercises, and specifically resistance training exercises, are the two Newton's laws of motion. The first one, or actually the second law of motion, which is the law of acceleration, and the third law of motion, which is the action-reaction law of motion. In the following slides, I will elaborate further a bit more about these two motion laws, and finally you will understand how actually the movement itself is determined, or it's the result of both the magnitude and the orientation, the direction of the specific forces involved or underpinning the movement itself. So first, let's consider how actually the magnitude of forces is able to specifically influence and determine the characteristics of a movement. According to the second law of motion, or law of acceleration, which is reported here in the top of the slide, there is a direct relationship between the force F and the acceleration A, where actually M stands for mass, which is the mass of the body or the mass of an external object if we're talking about a specific exercises oriented or focused, finalized to move an external object. So using an analogy, what we would do in order to understand better the second law of motion is to consider the mass of the body or the moving object as the resistance, the external resistance you would like to overcome or you would like to move during the specific motor task, while the force can be considered as a sort of potential, the investment in energy you're going to apply when aiming to perform a specific exercise. And finally, A, the acceleration, is the specific output you are able to achieve. So there is a clear relationship between these three elements: the resistance, the potential you're going to invest, and the output. Now, from the basic rules of physics and mechanics, we can break down the acceleration into the two main subcomponents, where actually the acceleration is commonly defined as the rate in change of velocity over time. So delta V means change in velocity, and delta T means change in time. So the acceleration is actually how the velocity is going to change over a given time window. Following this step, we can actually move the delta T component to the left hand side of the equation, and we are going to consider the second law of motion as the relationship between the impulse and momentum. Again, I'm going to use a sort of analogy to help you understanding and help you, let's say, recalling later on this formula, and to understand properly how forces produced by the body with the aim to move the body itself or with the aim to move an external object actually determine the specific outputs, the specific outcome in the movement. So let's consider first the left side of the equation, where F, which again means force, is multiplied by delta T, which is the amount of time during which the force is applied. In physics, mechanics, and biomechanics, the combination of force and time is called impulse. And using an analogy from the economics, the financial field, we could consider again the impulse as the investment the body put in the movement. So the total amount of energy, the total amount of force the body is producing with the aim to accomplish a specific movement. On the other side, as defined earlier, the mass is the resistance, but the combination of mass and change in velocity, delta V, is commonly referred as to momentum. So momentum is the change in velocity of the moving object, which can be either our body itself or can be an external object. So I can give you two basic examples. In a body weight exercise, we can apply forces onto the ground while standing in a steady position, and we can start or begin moving with the aim to walk, with the aim to jump, with the aim to sprint. The same approach can be used to describe the movement of an object, let's say a medicine ball throw, where forces are now applied from the body and transferred from the body, usually the upper limbs, to the medicine ball, and finally the mass of the medicine ball is gonna be accelerated, so it's gonna gain and gather some velocity before it's released by the arms. Well, two important conclusions actually come up from the second law of motion. The first, that which is very let's say basic or basilar. So the greater the force produced, so the higher will be the impulse, the combination of force over time, the greater will be the change in motion. So higher level of forces or greater amount of forces across time will determine an increase in momentum. And this relationship is positive and linear. So higher forces, greater change in motion. Another important conclusion we can, let's say, consider or take into account from this relationship is the fact that force and delta time, or the window of time during which force can be applied, are in an inverse relationship. So let's say that we have a final output of, just give you a made-up number of 100. So the total momentum at the end of the motion would be 100. Don't care, doesn't matter right now what is the measurement unit. This 100 actually can be the result of 20 units of force by 5 units of time. So we have a large amount of forces produced during a relatively short or low duration in terms of time of the movement. But actually the same result can be accomplished with only 5 units of force through 20 units of time. In this case, you will imagine that the movement itself is much smoother, it's less sharp, so we have less forces for a longer duration. In this case, we would imagine that the second example I've shared with you is that representing a movement which is not performed in an explosive manner. Well, another very important law or rule we should take into consideration when prescribing exercises is the third law of motion, commonly defined as the action-reaction relationship. So, based on the action-reaction relationship, whenever we're gonna produce forces and apply these forces into a direction, we're going to receive back the same amount of forces in the opposite direction. So just to give you a basic example, imagine yourself standing steady in a standing position. You're going to push with your left leg, with your left foot onto the ground to the left in order to move your body to the right. So actually you are producing forces against the ground. These forces are oriented to the left, but actually the result of this action is a movement to the right. The same applies for walking tasks. When we start walking, we begin to move. Actually, we push with our feet onto the ground backward in order to move our body or to accelerate our body forward. So this means that there is a specific relationship between the direction, the orientation of forces produced and the final outcome in terms of movement. And this is something that obviously we should take into account when prescribing exercises with the aim to create a specific transfer effects if the exercises are finalized to improve functional or motor performance capabilities. To give you an example, let's assume that our target population is represented by basketball players, and we well know that one of the key movement determinants for basketball players is vertical jump ability. As a consequence, we would like, as strength and conditioning practitioners, to plan and prescribe exercises into a gym environment finalized to improve this important capability, which is the vertical jump one. And as a consequence, we are gonna put into a plan some exercises which have the same force orientation. One possible option could be a back squat. Another possible option could be a deadlift. On the opposite side, on the contrary, if our aim is to improve abilities like change of direction, like acceleration or sprints or sprinting, we should definitely reconsider our choice and select some exercises which have the same correspondence and same similarities, so actually which resemble the specific forces demands of this task. So as an option to improve acceleration capabilities or change of direction capabilities, we should do some exercises in which the body is demanded to move forward or sideways rather than vertically upward. Well, once defined the let's say key elements or the key definitions of force and the specific rules or specific laws we should take into consideration when assessing, analyzing or prescribing exercises, we can then move on and we can consider the specific determinants and mechanisms underpinning force production. So actually these mechanisms or factors can be categorized into three main categories. And the first category we're gonna consider is that more related to morphological characteristics, so the structure of the specific units dedicated to produce force, which actually are the musculoskeletal units. So, first, we well know that there is a direct relationship between the physiological cross-sectional area and the ability to produce force. So this is actually what bodybuilders try to achieve when cautiously programming and planning their training workouts in the gym. They try to increase as much as possible the masses of their muscles, with the aim to be able to produce at a later stage a greater level of forces. So we know that there is a clear relationship, a direct relationship between the cross-sectional area. So if you like if we take a slice of the muscle, we can measure the total amount of the mass of the specific muscles itself, and the amount of force or the force capability this muscle is able to produce. Well, another key determinant of force production is the Pennacial angle. For definition, the Pennacial angle is the angle determined between the muscle tendon and the fibers themselves. So in this case, we would imagine that the Pennacial angle of this specific muscle, the rectus abdominis, is actually zero. So there is no Pennacial angle because the long axis of the muscle fibers and the tendon correspond to each other, so align to each other. Let's consider the second case. So this is the axis of the tendon, and this is the orientation of some of the fibers. So you can see that there is an angle created between the two, this angle, which is commonly defined as Pennacial angle. And moving so on and so forth, we can actually draw the same for the other two muscles. In general, the general rule we should consider is that the greater the Pennacial angle, or the more, let's say, acute the Pennacial angle, the greater is the ability to produce force from that specific muscle. And obviously this is something that we should take into consideration, because we know that there are specific muscles which by the mean of their morphological characteristics and the Pennacial angle that they are able to create with their specific tendons, will be able to produce a higher or greater level of forces as compared to other muscles, which can be co-synergistic muscles, can be antagonist muscles. So we should be able to understand what is the interplay between muscles in the same muscle group, between agonist-antagonist groups, acting actually on the same joint but determining and underpinning opposite movements. Well, the next factor we should take into account, which can have a massive role in determining force production capabilities, is the isoform of the myosin heavy chain. I do remind you that myosin is one of the contractile proteins responsible for the let's say these sliding and cross bridges effects within the muscle, leading to force production. So depending on the specific isoform characteristics of the myosin proteins, we can classify, we are usually classifying the muscles in the three main categories. Type 1, which are the so-called red muscles or slow twitch type muscles, usually dedicated to perform activities more oriented to resistance, endurance capabilities, sorry. So like running, long distance running, cycling, or rowing. While type 2A and type 2X are commonly defined fast twitch type fibers or white fibers. So these are the fibers dedicated to produce a very high amount of forces in an explosive manner, but the downside is the fact that these fibers are easily and quickly fatigable. So actually they can easily and quickly lose their force capability because of the effect of acute fatigue. Well, now moving on to the second category of factors influencing force production, we have to consider the neuromuscular factors underpinning force production, which partly are taking place at the higher levels of a hierarchy in the neural system, so at the brain level, and in the areas where actually the movement, as I mentioned earlier, is designed and planned, and some other mechanisms which actually happen at peripheral levels, so at the level of the muscle itself, and specifically at the level of the neuromuscular junction. So first of all, we well know that force production, especially for complex motor tasks, it's a combination of many muscles brought together to act like a team to contribute together in the development of the overall force output. So this is commonly referred to muscular units recruitment, so the ability of the neuromuscular system to recruit as many muscular units as possible to cope, to face with the specific motor task. In this regard, it's very important to remember that the neural system uses some strategies when determining the specific, I would say, amount or number of motor units to be recruited in order to accomplish a specific task. This principle is commonly referred to the size principle, where actually the motor units of small dimension, so those with less force production capabilities, are initially recruited to accomplish the task, and only in case the total amount of force they are potentially able to produce will not be sufficient to cope with the task, this leads to the recruitment of additional motor units. So according to the science principle, first the small motor units are recruited and then the bigger ones. As a second important element to be considered for the muscular motor units recruitment is the rate coding. So actually the same motor unit can be recruited with an incremental frequency, and this again depends on the given force demands associated to the task to be performed. So let's assume that we are comparing the same task, which is let's consider squat exercises, performed into two different variants. So the first one with a very light external load, let's say 20% of the maximal capability of a given subject, and the second variant is performed with a very heavy load, 80%. So despite the same motor task, the same exercise, the same mechanical demands, so the ability to develop force vertically onto the ground, assuming a relatively comparable technique for both exercises, obviously the different demands in terms of force production, so the differential percentage between the two variants, is going to determine a specific and different motor recruitment pathway, where in the first case, for the 20% load, probably the neuromuscular system is going to recruit the smaller motor units with a low frequency, while in the second case, when the demand is to lift 80% of one maximum repetition, it's most likely to happen that the bigger or the greater motor units are going to be recruited with a higher frequency of coding. Another very important element to consider is the so-called co-activation or co-contraction phenomena in muscular recruitment and muscular contraction, which can be considered either as a strength and a weaknesses. In fact, let's consider the same example I've just given, so the squat exercise. We well know that some degree of co-contraction or co-activation is required in the squat exercise between, let's say, the knee extensors, so the quadriceps muscle, and the hip extensors, so the glute, the extensors of the hip. So these muscles should work in synergy, co-contracting in order to complete the specific task, which is lifting the barbell placed over the shoulders blades. But the same co-activation, same co-contraction element can be considered sometimes as a weakness. Let's consider another common task in sport, which is a football kick. So consider the football kick and primarily the movement occurring around the knee joint, so the flexion extension of the shank across the knee joint in the kicking action. We would presume that a lack of synchronization or a dysfunctional co-contraction and co-activation between the agonist muscles, which are again the four single muscles creating together the quadriceps, and their antagonists, which are the flexors, the hamstrings. So a lack of synchronization and co-contraction can lead potentially to injury occurrences. And this is commonly observed in clinical studies when the quadriceps is relatively stronger or too stronger as compared to the hamstrings, and when kicking a ball repetitive times, many times during a week, during a training block, this can lead to dominance of the quadriceps, and this dominance of the quadriceps could cause eventually some negative effects on the hamstrings, especially when they are required to contract while lengthening during the kick with an eccentric force modality production. So in these terms, co-contraction can be, let's say, considered as a negative effect in consideration of two main elements. The fact that a lack of co-contraction or appropriate co-contraction can actually lead to injuries occurrences, and in other cases an excessive co-contraction can limit the force production capabilities of the antagonist muscles. In the latter case, I can mention a elbow flexion exercise, which is performed by the biceps brachii. During the flexion action, the antagonist effect of the triceps brachii can limit the force production of the antagonist, so the biceps brachii. Obviously, it's a more complex mechanism which can be partly modified through training, but overall we should remember that a co-activation or co-contraction is a sort of strategy the neural system puts in place to either prevent excessive forces which can lead to injuries, or as an inhibitory mechanism which again can limit some detrimental effects. Finally, another very important element to consider, which I already mentioned earlier, is the specificity between the task we would like, let's say, to improve, to enhance, and the exercises or the training mean we are going to use for that purpose. So there should be a resemblance between the exercises we're going to design and implement in our training sessions and the specific motor task we would like to have transference effects on, with the aim to improve it. Well, the last category of factors we should consider when let's say understanding what could be the limiting or potentiating mechanisms leading to force production is the relationship between the joint characteristics, so actually the configuration of the joint around which the movement is performed, and both the force and velocity relationships. So first we should remember that there is a specific relationship between the position of the joint acting and the ability to produce force. In fact, we know that the movement of the joint is the result of a torque production, where torque is a combination of force and the muscle arm. So in this case, we would imagine, and we all experienced these events, either in the gym or when, let's say, carry on a bag from a supermarket shopping, that the ideal position of the elbow joint to produce the greater torque is 90 degrees. 90 degrees actually is the position where the arm of this muscle is at its maximal length. So we know that there is a relationship between the force or the ability to produce force and the arm position of the muscle itself within the joint. So this relationship is clearly shown here when we can see that there is an optimal length or an optimal positioning where the muscle arm is maximal, and as a consequence the force production associated its maximum as well, while reducing or increasing the length of this arm, so by changing the joint configuration, in this case either extending the elbow a bit farther or flexing the elbow, then positioning the forearm bones closer to the humerus is going to reduce the force capability. Another very important element to consider is the relationship between force and velocity, and this relationship can be defined as an inverse negative relationship. Just to give an example, let's assume that we're gonna complete again our squat exercise, and performing the squat exercise in two different variants, two different conditions, both loaded with the same external load, so with the same external weight. We can either perform this exercise at low speed or at high speed. So the general rule to remember is that the higher the speed of movement, the lower will be the force production. Or actually, the lower the speed, the greater the force production. So there is a linear inverse relationship between force production and velocity of movement. Well, the last element or mechanism I would like to touch on in consideration of the force production factors is the relationship between PAP, which means post-activation potentiation, and fatigue, and the ability of the musculoskeletal system to produce force. So as a general definition, PAP represents a phenomena through which our skeletal muscles are able to produce their maximum force capability as a consequence of an ideal, optimal, comprehensive warm-up. So actually PAP is what we usually try to achieve when designing and planning as initial stage of a training session, a comprehensive warm-up. And we well know that there are some other mechanisms facilitating the PAP effects. So an increase in the muscle temperature, an increase of the excitability of the neuromuscular junctions, a change in the specific pennation angle of the muscles recruited and demanded to produce force. And there are also other psychobiological mechanisms related to motivation and affective valence, so something which is more associated to the psychological or underpinning psychological elements of force production. But actually we should remember that following a comprehensive warm-up, our force production capability is inherently increased. So there is a potentiation of a muscular task. However, on the flip side, in case the potentiation strategy, let's say the warm-up itself, has been not accurately designed, so probably it's been too long in duration, it's been too intense, it's not been completely addressing the task specificity demands, so we have done something which is not really related to the task that is gonna be performed later on during the training session itself. So we can actually lead to detrimental, to negative effects on the task. And this is commonly attributable, so this arises from the fatigue effects. We well know that After a warm-up session, especially if the warm-up session was not appropriate, we have a decrease in performance, which is a temporary decrease, an acute decrease in performance, and then only following an appropriate rest period, we can perform or we can conduct our task with an increased capability. So this is what commonly referred in the literature as the relationship between PAP, potentiation, and fatigue. Usually, potentiation occurs after a rest period. So following the warm-up, we should wait about 6-8 minutes in order to facilitate the potentiation effects or the beneficial effects led by the warm-up strategy. While fatigue occurs earlier, the time course of fatigue is quicker. Immediately after the warm-up, we should experience some decreases in the motor performance, which will be replaced later on by the potentiation effects.